looks at exploring the graph of a trig function, of the primary trig functions, sine, cos, and tan. So before we get started with graphing those, there are some terminology, some terms that we need to understand. First of all, we need to understand what a periodic function is. A periodic function is a function that starts to form a repeating pattern over time. That time being referred to as a period of time. And then we have the amplitude. And the amplitude of a periodic function is defined as half the distance between the maximum and the minimum values of that function. So if we look at the first class example, we're going to explore the period and the amplitude for each of the following periodic functions. So if we look at the first class example, we've got this function that definitely shows this repeating pattern. It goes up and then it comes down. It goes up and then it comes down. So the period of that function, if I start at 0 and follow the path, goes up, comes all the way down, then comes up again, this is where it starts to repeat. It started at the middle and went up. So if I look at how long this interval was, it went from 0 to 8 units. So the period is 8 units. Now if I look at the amplitude, remember from above, the amplitude is half the distance between the maximum and the minimum. So to find the distance between the maximum and the minimum, we subtract these two values. So 10 minus negative 10 gives me a value of 20. That would be the distance from maximum to minimum, would be 20 units. And I take half of that. So the amplitude ends up being 10 units. The other way to think of amplitude is if I figured out where the halfway mark of my function is, which in this case is the x-axis, it would be the distance going from the x-axis to the max or the x-axis to the min. But if I change where that midline is, that middle of the road, middle of the function, then it's going to change how I would do my measuring. So take a moment to pause and see if you can do B. Determine the period and the amplitude of B and then continue. So in looking at the period for B, a strategy that I would probably use would be starting on the 0 line. Starting at 0 and then checking to see when do I get back to that same spot again, which happens right here. So I end up with a period of 6 units. Now when I go to look at the amplitude, I take this maximum value, which was 6, and subtract the minimum value, which is negative 2. That gives me a distance of 8 units. It takes 8 units to go from the top to the bottom. Half of that becomes my amplitude. So I get an amplitude of 4. And if I was to look at this, this would be the middle of my graph. I go up 4 units and I come down 4 units. It's in the middle. Okay, so try that again with C. Okay, so when we look at C, we look at the period. Again, I'm going to start here. So I go to the right, then I go up, down, and come back down. Then I would go to the right again. So this ends up being 1 period, which is 10 units. And then my amplitude, I have a maximum of 6 and a minimum of 2. So that gives me an overall distance of 4, and I take half that value, and I now get an amplitude of 2. So what we are going to look at is we're going to look at these trig functions, sine x, cos x, and tan x. We're going to explore sine, and cos and tan are going to be questions in your assignment. So to investigate these, we're going to use a table of values on a domain from. So in this exploration of y equals sine x, We're going to be working in degree mode. So we have to grab our calculator and make sure our calculator is set to degree mode. And then what we're going to do is we're going to write in the values from 0 degrees to 360 degrees to 2 decimal places. So sine 0, sine 30, I think is the next one. Yeah, every 30 degrees. So sine 30, I get 0.5. Sine 60, I get 0.8660. So then I would record that one as 0.87. So I've got 0, 0.5, 0.87, and on and on. So take a moment, pause, and fill these in yourself, and then double check to see if these are the right values. Okay, so these are the values that you should get, so double check that yours are the same. And then the next thing that I want you to do is I want you to plot these points on this grid. Don't join the points, just plot them at this point in time. And again, when you're done, double check to see if they match up. So you should get something like this. So now what we're going to do is we're going to graph this on our calculator, and these are the window settings that we're going to use. So while you work on that, I'm going to work on that at the same time. Window settings are going to go from negative 360 to 540 degrees, going up at 30. So all of my tick marks will match from the grid to the graphing calculator. Negative 1.2 to positive 1.2, going up by 0.2s, which again will match. I'm in degree mode, so now I go to y equals, clear whatever I have there, and I'm going to graph sine x. And then you're going to press graph. And I get this wavy line. So what I want to do is I want to transfer this wavy line to the graph. So what I notice is I have these top points. And these top points happen at 90 degrees. And then I know that these are 30s. I know that this is 360. 1, 2, 3 units from 360 brings me to 450. So I know that I have a top end point here at 450. I want to make that one bigger. So at 450, I'm up here. 450, and then let's make that a little bit bigger so we can see it. Okay, and then I know that down here at negative 90, I'm at the bottom again. So again, I'll put a point there. At negative 90. At 180, I was at, or negative 180, I was at 0. At 270, I was up. And at 360, I was at 0. So again, I'm just going to make those all bigger. And those are kind of my guiding marks, because if I look at this graph goes up, down, up, down, up, down. So I'm kind of using these as my max and min pointers so that I can get this smooth curve. Oh, and I guess I forgot this one point. Let's see. Copy, and then we're going to paste it. And we'll move this right here. So now if I take a pencil and I join these together with a smooth curve, I end up with this type of a pattern. It doesn't have to be perfect. You're going to end up drawing this a lot in the next couple of weeks, so you're going to get a lot of practice, but you want to make it look like a smooth curve. Okay? This is a periodic function. This up-down wave is going to continue indefinitely to the left and indefinitely to the right. What I have here is I've just restricted it to this. But if I said that x could be anything, I could put arrows on the end of it, and because I've shown enough of a pattern, it should be a good enough indicator to whoever's looking at this that the pattern would continue to repeat. Okay? So now using this graph, we're going to state the following for y equals sine x, where x is defined on the set of real numbers, meaning x could be any value from negative infinity degrees to positive infinity degrees. So my domain would be just that. X is a real number. My range. So what is the range of the numbers? They go as high as positive 1, as low as negative 1. So y is between negative 1 and positive 1, with y being an element of the real numbers. Or I could use interval notation, negative 1 to positive 1. Then I have that amplitude. Remember we said the amplitude is the max minus the min. 1 minus negative 1, which is 2. And I take half of that, and I get an amplitude of 1. For my period, if I start at 0, the graph goes up, comes back to 0, goes back down, and comes back up again, and then I get that repeat. So it took 360 degrees to get that repeating pattern. So my period is 360 degrees. Then I have these x-intercepts. Where did this graph cross the x-axis? At 0, at positive and negative 180, and at 360 degrees, and on and on and on. So I could write this kind of as a, almost like a formula, where I could say, you know what, it's multiples of 180 degrees. The only thing I'm going to do is I make sure that n is an integer. If n is 2, I get 360. If n is negative 1, I get negative 180. If n is 0, I get 0. And then the y-intercept. Where does it cross the y-axis? At 0. Okay? So then the next part changes this. Instead of going from degrees, we're going to look at this in radian mode. So it says write down the graphing calculator window format the student should use. So from exploration number 2, my window settings were from 360 degrees, negative, to 540 degrees, going up by 30 degrees. And I want to change each of those into radian measures. So again, pause and take a couple of moments to figure out what those radian measurements would be. Okay. A hint that I can use to help me with converting these into radians maybe a bit faster is knowing that pi is 180 degrees and looking at these as kind of multiples of pi. So 360 degrees, that's 2 times 180. So that's going to be negative 2 pi. 540, if I go 540 divided by 180, I get 3. So that goes up to 3 pi. And then with this one right here, 30 divided by 180 is actually 1/6. So I get 1/6 pi, which is pi over 6. My window settings, those are for my x's. My window settings for my y's aren't going to change. They're going to stay at negative 1.2, positive 1.2, and 0.2. The amplitude is measured in decimal numbers and rational numbers. The domain is where I've got those pi's. So now if I was to sketch this on the domain from 0 to 2 pi, showing the intercepts, if I refer to the calculator, or if I refer to the diagram that's on the previous page, it took 360 degrees to get one full revolution. And at 180 degrees, it hit the x-axis coming back through and around. 360 degrees, that's my 2 pi. 180 degrees, that's my pi. Goes up, comes back, goes down, and comes back. I know that I have an amplitude of a positive 1 and a negative 1. It will not change just because I'm in radian mode. And these maximum points are halfway in between. So halfway between pi and 0 is pi over 2. Halfway between 2 pi and pi is 3/2 pi. So that would be an adequate enough sketch showing me the intercepts and showing me the general characteristics of this graph. So what I want you to work on is question 1, 2, and 3, and 6 to 11. And it'll bring you through explorations examining the cosine graph and the tangent graph.